Okay, so there's two fundamental roots for immunity. One is innate immunity. It is nonspecific. It is very fast acting. And we'll talk about it in detail momentarily. And the other is a little slower acting, but very specific, and has memory. It's called adaptive immunity. And it's what protects us long term. It is a strong immune reaction. It protects us a lot. It just takes time to kick in. They are distinct, but they work together, and they work simultaneously. So this video will be about the innate processes. So the innate processes are present at birth. The same processes, the same things will protect us against a lot of different types of threats. So it's very nonspecific. As opposed to the adaptive, which responds to specific threats. It's very specific. So the innate works almost immediately. So if we look at the total immune system, the adaptive is T lymphocytes, humoral and cell-mediated immunity, and it is geared for specific antigens, for specific pathogens. It's very, very effective. The innate, multiple components protect against a whole bunch of different things. Nonspecific. So the first line of defense is just the skin and mucous membranes, and then we look at cells, chemicals, and processes, physiological responses. We'll get more into that momentarily. So the best way to defend yourself is build a wall right along that southern border. Keep the drug dealers and murderers out. It's having an intact skin and mucous membrane, keeping the pathogens, the bad guys, out, is really the best way to defend yourself. But if pathogens get in through the skin or through cracks or cuts or anything like that, internally we have some things going on. And it really is either cellular with phagocytes or natural killer cells, non-cellular, non-living, extracellular stuff, chemicals really, interferon and complement, or physiological processes like fever and inflammation. So keeping the skin intact, the best thing. But skin and mucous membranes also have secretions. There's something called the acid mantle, that bacteria don't like acid. There's lysozymes, there's secretions on the skin, on the mucous membranes, that also help protect. Various like natural antibiotics in saliva and such like that kind of thing. Okay, the cells that we're going to talk about, the first and the most important ones are the phagocytic cells. And the most important phagocytes are the neutrophils and the macrophages. There are dendritic cells, there are eosinophils have a certain role to play in it, and various other things. But really, the two major phagocytes are neutrophils and macrophages. And they really just gobble up any unwanted substances. They just do phagocytosis. And they're not picky about what they eat. So they'll eat cellular debris, pathogens, viruses, proteins, anything that's not supposed to be there, they will eat up. They take it in through endocytosis, phagocytosis. They digest it, and then they, through exocytosis, they put out the amino acids or whatever was left over. Now, all of these things will also work in the adaptive immunity as antigen-presenting cells. We'll talk about that in the next video. Really, the only way to get rid of pathogens is through phagocytosis. Everything else we're going to talk about for the next two videos is really about enhancing the macrophages and the neutrophils' ability to eat, to phagocytize these pathogens. So this is what it looks like. It gets engulfed, it gets broken up, and then the residue is dumped out. Other cells are involved. They are pro-inflammatory mast cells and basophils. They release chemicals that like histamine and heparin that are very useful in the processes, in the fever and in the inflammation. Okay, there are natural killer cells. These are a nonspecific type of lymphocyte, and their job is to kill any of your own body cells that have something wrong with them. So they will kill worn out cells that aren't behaving properly. They'll kill cancer cells. They will kill any cell that is infected with a virus, so virally infected cells. They perform kind of immune surveillance. They patrol the body, they look for unhealthy cells, and they destroy them. What they do is they come up next to them and they release a chemical called perforin, which perforates the cellular membrane and induces apoptosis, the killing your own body cells. We use eosinophils to attack multicellular parasites, and they're part of the cleanup crew, but we won't get too much into it. Basically, eosinophils come to like a worm or any multicellular parasite and basically throw up on it and then digest it from the outside in and kill it, cytotoxic. Okay. So the two fundamental types of cells, phagocytes, which are neutrophils and macrophages mostly, and natural killer cells. The two processes that we're going to follow are inflammation and fever. So inflammation first. It's a response, local response. It's nonspecific. All kinds of different things will give you inflammation. It doesn't become systemic. The vascular tissue in the area of injury vasodilates. What happens is as tissue is damaged, damaged cells release chemicals that cause mast cells and basophils and things to, like histamine and leukotrienes and prostaglandins, that are all going to be useful in healing. But they are all pro-inflammatory chemicals. They will cause inflammation. So these chemicals cause vasodilation, and then with the vasodilation, more blood stays in the area. And capillaries become more permeable. So what happens is the white blood cells that are circulating in the blood end up sticking. It's called margination. They adhere, and then they migrate out into the tissues between the cells. It's called diapedesis. And then they follow the chemical trail to the site of injury through the interstitium, through something called chemotaxis. Chemotaxis, chemicals that carry you to a destination, taxi. They also will release pyrogens, which pyrogen generates fire. It's the fever inducing molecules. So when this vasodilation happens, what that extra blood brings is nutrients, oxygen, antibodies, and immunoglobulins, the clotting proteins, complement proteins, all kinds of things that are useful. There tends to be a release of chemicals that cause pain. So it makes you stop using it. It makes you stop doing the thing that got you the tissue damage to begin with. This excess fluid becomes important, and we end up with all this excess interstitial fluid. And what that does is it brings immune cells to eliminate the pathogen, and it brings nutrients and things to promote healing. That extra fluid gets picked up by the lymphatic capillaries, which then is going to pull this debris and any pathogens into the lymphatic system and get them to the lymph nodes where they can be attacked and dealt with. Now, the macrophages eat bacteria, damaged cells, they even eat dying other phagocytes. Now, as lay people, we tend to think, and even as medical professionals, we think of inflammation as a bad thing. It's really not. I tell a story of my son having a party when he was a teenager, and it got a little bit out of hand, and there was a hole punched in the drywall of the family room. And we were out of town, and when we came back, the boys had tried to fix it by putting drywall mud in the hole and trying to take care of it. And it looked like shit. It was a terrible repair. So what did I do? I cut out the hole and all the damaged drywall around the hole, and I made the hole much larger. I got back to good undamaged drywall, and then I put a new piece of drywall in, taped it, mudded it, sanded it, and then primed it, and then painted it. So I had to do more destruction before I made the proper repair. If you have a little rust hole in the door of your car, you bring it to a body shop, they take all the paint off the whole door, and then they make the hole a lot bigger because they cut back to good metal, then they weld in a piece, and then they put the Bondo and sand, and then they repaint it. So to make the proper repair, you have to remove things. So if you cut yourself, there's the tissue that's dead, and then there's the tissue that's damaged around the dead tissue. You have to get rid of all of that back to good tissue before you're going to get a decent repair. Inflammation also sequesters the pathogens in an area. It prevents it from spreading because the pressure kind of holds liquid in place. Now, there's 5 cardinal signs of inflammation. Your book calls the one loss of function, but the mnemonic to remember is PRISH, P-R-I-S-H. P is for pain. Pain comes from the stimulation of pain receptors. That happens because of the compression of the extra fluid. It happens because of the prostaglandins and other chemical irritants. And so you end up with pain. And that's a useful thing. It makes you pay attention. It makes you avoid doing it. R is redness. It's red because there's more blood in the area. It's as simple as that. So there's more fluid because there's more blood. There's more redness because there's more blood. I is immobility or loss of function. And that's really from the pain and the swelling. And what you do by immobilizing an area through inflammation is you prevent the pathogens from getting into circulation. You kind of sequester it, you keep it there. P-R-I-S. S is for swelling. And the swelling comes from an increased fluid in the interstitium, which comes from increased capillary permeability and more blood coming to the area. H, it stands for heat, and that's because of the increased blood flow. Blood is warmer than the tissue, so it gets hot. So what you have is P-R-I-S-H, pain, redness, immobility, heat, or swelling and heat. Now, acute inflammation should last a week or 10 days. Once it gets beyond that, what you start to end up with is histological change, and that's called chronic inflammation. And that may or may not have more detrimental effects. So, inflammation, the bottom line is inflammation is good. Fever is also good. So, fever is the result of the release of pyrogens. Pyrogen generates heat, interleukins, things like that. So what's going to happen with fever? The pyrogens get to the hypothalamus. The hypothalamus releases some prostaglandins, but it raises the temperature set point, and body temperature goes up. So you have the onset, and then it flattens out, and then it goes away. This heat promotes the elimination of harmful substances. It makes you bind zinc and iron, which are both necessary for microbial reproduction. So it slows the reproduction. It speeds up phagocytosis. It speeds up healing. It speeds up the metabolic rate of your own tissue. So it's all very good. Then it gradually goes away. My wife and I, when the kids were small, she always wanted to break a fever early, and I always wanted to let it go because I'd rather see the kids really sick for a day and a half than kind of sick for a week. So this is all the things that it does. If you're going to leave a fever, though, you've got to monitor it because it can get too high. If it gets too high, it can have some damaging effects. You can get denaturation of proteins. You can lose the effect of enzymes. You can get brain damage. Neurons can be damaged, and that kind of thing. But a low fever is a good thing. So we didn't get to complement and interferon. I don't know why there's not a slide on that. So what complement is a series of proteins, complement proteins. There's a bunch of them. And they do a bunch of things. But for a cellular pathogen like a bacteria or a protozoan, what happens is these proteins get inserted into the cell membrane of that cell, of the pathogen. And all of these proteins, when they get put in there, float together and they form a ring. And that ring basically pokes a hole in the bacteria, and if it doesn't kill it, it wounds it, slows it right down. We call this the membrane attack complex. So it really causes lysis of cellular pathogens. Very useful thing. And it doesn't matter what bacteria, it will do it to a streptococcus and bacillus and anything. Like, it doesn't matter. So it's non-specific. The other things that happens is that when the complement proteins get inserted, they cause a release of pro-inflammatory chemicals, so they enhance inflammation, if not outright start it. And we just saw that inflammation is good. And the other thing that they do is they enhance phagocytosis. And I've already said that the macrophages and the neutrophils are the things that actually eat the pathogens. So what they do is they engulf the pathogen. But if it's a bacteria, as the macrophage goes to engulf it, it can just swim away. So the complement protein adheres to the macrophage so that the bacteria can't get away while it's getting engulfed. It's like if you're at a bar and the bouncer is going to punch you, he grabs your shirt so you can't avoid the punch. The complement is the shirt. The complement is the thing that gets grabbed and holds the bacteria in place while the macrophage engulfs it. So complement, the membrane attack complex, enhances the phagocytosis, and enhances inflammation. Now, interferon interferes with viral replication. When a virus enters the body, it goes into specific cells that it's adapted to enter, and it takes over the transcription and the translation of protein synthesis. So a virus being just a protein coat with a piece of DNA in it, or RNA, what it does is it goes in, the DNA or RNA replicates using the transcription mechanisms of the cell, and then that goes to the ribosomes, and the protein synthesis becomes the protein coat of the virus. And so the virus takes over the protein synthesis to stop making the protein it's supposed to and start making viruses. So if it's a liver cell that's making albumin, it stops making albumin and starts making viruses. So what happens with that is the cell can't do anything about it. It's been taken over. But when it's not making the right proteins, it releases a chemical called interferon. And what interferon does is it goes into all the cells surrounding the infected cell, and it shuts down their protein synthesis. They stop making proteins altogether. So that if a virus, so when the first cell bursts open from having so many viruses in it, macrophages eat them in the interstitium, but some of them get into all the neighboring cells and they grow exponentially. But not if they get into the neighboring cells and there's nothing to take over. So interferon slows the reproduction of viruses. However, it makes the cells useless, so they're not making the proteins that you need. So you feel like shit but at least you slow the virus. And eventually, the macrophages will, and so enough of these virus-laden cells will be killed by the natural killer cells and broken open, and the viruses will be in the interstitium, and the phagocytes will eat them until they're finally gone and you have no more infection. So to summarize, we keep the barriers intact as the first line of defense. The second line of defense, there's two types of cells, the phagocytes and the natural killer cells. There's two processes, inflammation and fever, and there's two extracellular proteins that are really important. Complement proteins for cellular pathogens and interferon that interferes with viral replication.